Hi, this is Yilmaz Sozer from University of Akron. I'll be presenting our Open Innovation Fund project for Power America. The project title is Silicon Carbide-based Power Electronic Driver for Electric Vehicle Traction, and the Borg Warner is our commercialization partner for the project. Here is the brief overview of the project. Motor drive development for electric vehicle traction is challenging to get the higher volumetric and gravimetric power density, reduce system cost, and increase the system efficiency. Power electronic inverter integrated with the multi-phase electric machine would reduce the cabling, provide a better thermal performance, and a compact motor drive system. 210 kilowatt silicon carbide based inverter with the 6-phase ferrite magnet machine integration is proposed in this project. With the use of the silicon carbide inverter, high bandwidth capability will be achieved. It will reduce the size of the filtering elements, improve the electric machine performance, such as the reduced torque ripple, higher efficiency, and lower acoustic noise. So overall system will get very good efficiency, small and compact design, and a better thermal performance. The aim is to be able to fit into the electric vehicle a dedicated space for the motor drive. 6-phase permanent magnet machine is made of two 3-phase winding sets placed into the electric machine. Mechanically, there's a 30-degree phase shift between the winding sets. To be able to model the machine, two individual DQ model is chosen, and each DQ reference frames are 30-degree phase shifted from each other. The resultant DQ equivalent model shows that there is a coupling between the phases, and that mutual coupling would contribute to torque generations as well. So based on the initial finite element analysis and the dynamic simulations, we have seen a 445 Nm average torque using close to 300 amp RMS and then 400 amp, 112 amp peak currents. So that analysis is going to help to assess the drive operations and then select the components accordingly. In addition, we have achieved a coupled simulation between the power electronic drive and finite element machine simulations. So we can see higher order harmonics in this on the back EMF voltage, which is affecting the torque generations and the phase currents. So better control strategy can be adopted to suppress the effect of the higher order back EMF harmonics. One thing we achieve in this project is the phase shifting between the individual drive sets, which reduces the overall DC bus ripple current, and it provides better packaging options. As we see in this graph, the peak-to-peak ripple current on the DC bus current is significantly reduced when we apply the interleaving between the individual drive sets. That's have a very good impact on the amount of the capacitor required for the DC bus voltage. Based on the drive simulations, we have demonstrated that the amount of capacitors required for the drive is significantly reduced by using interleaving between the individual 3-phase drive sets. We also demonstrated that going from 20 kHz to 40 kHz using a silicon carbide modules also reduced the amount of DC link capacitor required for the drive. So we determined the RMS current, RMS phase currents, RMS device currents, the battery currents, and the ripple to be able to size the inverter. The comparison between the silicon carbide modules and IGBT modules demonstrated that we can reduce the volume and improve the efficiency significantly compared to the IGBT modules. We have followed the finite element based printed circuit board design approach. both in analyzing the design and also using that analysis for the optimization of the design. So finite element-based printed circuit board modeling for computation loop inductance and the capacitance extraction is achieved. Exact replication of the DC-link high-frequency capacitors are developed and included into the model. Module connectors and the DC connector vias are modeled accordingly. The parasitic capacitance calculation between the module connectors to base plate to cold plate with accurate dielectric material modeling is achieved for analyzing the overall printed circuit board. For the optimization of the design, we did the layer sequence optimization. The ceiling and the high frequency capacitor placements are optimized for minimizing the loop inductance. We have achieved connector modeling. Both thermal performance and mechanical structural performance is analyzed and optimized. And then we have achieved a planar inductor design for the output filters, which is also achieved through rigorous finite element-based modeling. So current distribution is shown here through the simulations. So what we have seen that if we share the density between the planes equally, then the flux cancellation between the layers can be achieved for minimizing the loop inductance. And current distribution can be modified by optimizing the high frequency capacitor placements that will increase the mutual inductance between the printed circuit board's trace and module return path, so we can achieve a lower overall loop inductance. Here we can see the switch transient modeling and its simulations, and then we can see the performance of the switching actions with and without the optimization of the loop inductance and the PCB layers. With modeling of the parasitics in the drive, we have designed an EMI filter. Here we can see the performance of the drive with and without a common mode filter. You can see that the common mode noise and the differential mode noise are significantly reduced using the common mode filter that we have designed. For the gate driver, we have achieved fast overcurrent protection, active Miller clamp, under voltage lockout, shoot-through protection, and isolated module temperature sensing. For the control board, we have included the phase and battery overcurrent detection, active noise filtering circuits for the sensors. We have included the PCB-based shielding for the PWM traces, resolver-based position sensing, and CAN communication. Mechanical enclosure design provides a base plate to be able to place the inverter on top of the electric machine, cold plate to provide the cooling for the modules, and the cores for the inverter output filter. We have designed our cold plate to be able to extract the heat from the inverter modules and inverter output filter. So we have included 8 passages to maximize the heat extraction, and then we included the O-rings to eliminate the leak of the liquid from the cold plate. The face cover will be attached to the cold plate. Based on the inverter operation and the cold plate design, we have conducted a finite element-based thermal analysis. The highest temperature in the structure was found to be 65 C, which occurred on the power board. So we have concluded that the cold plate design and the coolant flow will provide a good safety margin. Here is the 3D view of our final design. You can see the power board, gate driver boards, control board, communication links, inverter output filter, the modules, cold plate, the caps. In this view, you can also see the input EMI filter. Overall, we have achieved 25.84 kilowatt per liter volumetric power density. Currently, we are working on the build of the hardware and machine and dynamometer interface design and embedded control programming. Eventually, we will be testing the integrated drive on our dynamometer at the University of Akron. If you have any questions, please feel free to contact me. My email address is ys@uakron.edu. Thank you.